Welcome to the deep dive. Today, we're looking at a paper that really shakes things up a bit in how we align language models for everyday conversation. We're diving into reinforcement learning with model-rewarded thinking, or RLMT.
Yeah, this is a really interesting one. It tackles something folks in AI have been wrestling with for a while. How do you take reinforcement learning reasoning, which works great for things like math or code, where you can clearly check the answer?
Yeah.
How do you get that kind of reasoning power into more open-ended stuff, like drafting an essay outline or even just creative writing?
Exactly, because that kind of structured thinking, what some call chain of thought or COT, it's typically been stuck in this niche they call RLVR, reinforcement learning with verifiable rewards. And the core idea behind RLMT seems almost, well, simple at first glance. Force the model to spit out a thinking process, a trace, before the final answer.
Right. But here's the twist. Instead of checking that thinking with some hard rule, you optimize the whole thing using a standard preference reward model, the same kind of reward model we already use in RLHF, judging the quality of the final response.
And the results they got are pretty eye-opening. Across the big chat benchmarks, Alpha-Chi-Vol 2, Wild Bench, Arena Hard, these RLMT models jumped up significantly. We're talking like 3 to 7 points better than the usual baselines.
Yeah, substantial gains. And the real kicker, they got a smaller model, a Llama-3.1-8B, trained with this RLMT approach. And it actually managed to beat models like GPT-4o on some chat and creative writing tasks.
Which really makes you question the standard playbook, doesn't it? That whole complex, multi-stage training pipeline with tons of supervised fine-tuning data. Maybe it's not always necessary.
Exactly. It hints that if you cleverly incentivize this explicit planning within the optimization loop, you might unlock serious capability with potentially much less data and smaller models. So that's our goal today, really, to unpack how they made that incentive structure click.
Okay, let's set the scene a bit more. Why is this problem RLMT is tackling so important? Humans, when we face something complex, like planning a project or writing something persuasive, we engage in what psychologists sometimes call System 2 thinking. It's that slower, deliberate, step-by-step reasoning.
Right, and we want LMs to be able to do that kind of thinking generally, not just for specific verifiable tasks. The problem with the older RLVR approach was exactly that it was too domain-specific. RLVR uses these rule-based rewards.
Like, if it's a math problem, the reward is just, did it get the right answer, yes or no?
Precisely. Is 6x plus y correct? Reward 1 if yes, 0 if no. Mathematically, it's often written as like $1 y, while a, where that is the known ground truth answer.
Makes sense for math or maybe code that needs to pass unit tests.
Sure. But the models trained this way just didn't generalize well. The paper points out, and this is key, that RLVR models trained heavily on math problems actually did worse than standard instruction-tuned models on general chat benchmarks like Wild Bench. The reasoning skill they learned just didn't transfer.
Because there is no single ground truth when someone asks you to, I don't know, suggest a meal plan for their kid who's a picky eater.
Exactly. So the challenge is, keep the structure, the explicit thinking trace, let's call it Citadel-Lisbro, but use a reward system that can handle subjective quality, like the preference models used in RLHF for the final answer. How does RLMT actually connect that thinking step to getting a better final answer?
Right, what's the actual mechanism?
Okay, so RLMT makes the language model, let's call it policy, generate both things together. The reasoning trace is straight and the final answer, you're one. It's one continuous output sequence based on the input prompt, $6.
So you're sampling the pair Y and Z from the model. The thinking is mandatory, but the content of the thinking is up to the model.
That's it. Now, the crucial part, the reward function, toilers, is one of those preference models trained on human judgments of what makes good response. And importantly, it only scores the final answer, $5. So the reward is just $3. The objective then becomes maximizing the expected reward over the model's policy. Hang on, though. If the reward dollar only looks at the final output dollars, how do we know the optimization is really improving the thinking part? Couldn't the model just learn to produce slightly better dollars without necessarily improving Zealers, maybe just through some random gradient luck? Is this just RLHF with extra steps?
That's a really sharp question, and it gets at the elegance of the end-to-end optimization here. Because Zealer is generated by the same policy that generates Zeidel, the gradients flow back through the entire sequence. The model learns, through trial and error during RL, that the most reliable path to generating a high reward dollar is to first generate a well-structured, relevant thinking trace, Seidel dollars.
If it tries to generate garbage for salse or skips the thinking, the resulting in dollars is likely to be poor quality and get a low reward. So the policy gets pushed towards producing good planning in Zilla$ because that's the best strategy it finds for maximizing the reward on Llers. The thinking Ziller becomes this kind of optimized internal step, implicitly rewarded by the success of the final output.
That makes sense. It's not directly rewarding the thought itself, but rewarding the outcome that effectively requires good thought. Okay, let's talk implementation. They tried a few different online RL algorithms, right? DPO, PPO, and something called GRPO.
It did. Direct preference optimization, DPO, proximal policy optimization, PPO, and group relative policy optimization, GRPO. And the results there were quite clear. GRPO consistently came out on top. It beat PPO by about 1 to 3 points on average, and DPO by around 5 points.
Okay, GRPO. For our more technical listeners, why might group relative policy optimization be particularly suited for this task? With the long thinking trace, what makes it different from PPO or DPO?
Good question. GRPO is based on this idea of group-centered advantage estimation. Think about it. With PPO or DPO, you're usually calculating the advantage based on individual trajectories or steps. But here, you've introduced this potentially long, complex, variable planning stage. This adds a lot of variance to the trajectories.
Right. The thinking steps could be short or very long, depending on the prompt.
Exactly. GRPO is designed to handle that kind of variance better. It sort of looks at the advantage of the whole group, the thinking and the response together, relative to other groups. It seems to provide a more stable learning signal when you're optimizing these long, structured, high-variance sequences that include explicit reasoning. It smooths things out.
And that provides some real intuition for why that specific algorithm choice mattered. What about the reward model itself? Did any generic preference model work?
No, that was another critical finding. They found they needed a strong reward model. In their experiments, Skywork V2 was key. When they tried using weaker reward models in their ablation studies, the RLMT setup struggled. It couldn't maintain performance on other tasks while boosting chat performance. You really need a reward signal that's sensitive enough to distinguish subtle differences in quality that arise from better or worse planning.
Okay, let's shift to how they actually implemented this, because the efficiency angle here is really interesting. They had two main paths, a warm start and a zero training approach.
Yeah. The warm start is pretty standard practice. They first did some supervised fine-tuning, SFT. The goal was just to teach the model the output format they wanted, like having it generate text inside think tags followed by text inside response tags.
How'd they get the data for that?
They basically prompted a powerful existing model, Gemini 2.5 Flash, in this case, to generate examples of thinking traces followed by responses. So the SFT phase just taught the model the structure before they started the RL optimization.
Right, pre-training the format. But then there's the RLMT zero approach, which sounds, well, potentially transformative for how we build these models.
Absolutely. This is maybe one of the most striking results. They took base models like Llama-3.1-8B base and Qwen-2.5-7B base, which haven't gone through any instruction tuning or alignment SFT, and they applied RLMT directly. No SFT stage at all. They just gave the base model a fixed instruction in the prompt, basically telling it, think first, then respond, and then launch straight into the RL optimization using the preference reward model.
Okay, let's contrast the resources needed here. You have something like the standard Llama 3.1-8D instruct model, which goes through this huge complex pipeline, potentially using, 25 million or more examples just for the SFT stages?
Right, a massive data set and multi-stage process. Compare that to the Llama 3.1-8B base model trained with RLMT 0. They used only around 7,000 prompts for the entire RL training phase. That's it.
7,000 prompts versus potentially tens of millions.
Exactly. And here's the punchline. That Llama RLMT 0 model, trained with minimal data directly on the base model, actually outperformed the heavily trained Llama 3.1-8B instruct on the chat benchmarks by about 5.5 points on average.
Wow, that's huge. It suggests that maybe a lot of the capability for good conversational interaction and following instructions can be unlocked much more efficiently just by focusing the optimization pressure directly on this rewarded thinking process, potentially skipping enormous SFT stages.
It's profound evidence, yeah. It shows RLMT can be a very efficient way to achieve alignment and chat capability, leveraging the base model's inherent knowledge much more directly.
Okay, let's dive into those quantitative results a bit more. The benchmark scores really tell a story.
They do. As we mentioned, those average gains of 3 to 7 points on wild bench, WB, Alpaca Eval 2, AE2, Arena Hard V2, AH2, over standard RLHF were consistent across different models and algorithms. If you look at a specific model like the Llama 3.1-EB that was instruction tuned, then trained with RLMT using GRPO, it hit a score of 58.7 on Alpaca Eval 2, which is very strong for that size.
And how did it stack up against much larger models?
That's where it gets really interesting. That 8B RLMT model comfortably beat instruction-tuned models 10 times its size. We're talking Llama-3.1-7B instruct and Qwen-2.5-7B instruct. The 8B model was beating them by margins of 9 to 22 points on chat benchmarks.
9 to 22 points from an 8B model against 70B giants.
Yeah, and comparing against the closed frontier models, that same 8B RLMT model beat GPT-4o on chat and creative writing benchmarks. Its performance was also getting close to Claude 3.7 Sonnet, which is itself known for employing sophisticated internal reasoning or thinking processes, likely with far more resources.
And this thinking ability wasn't just limited to chat, right? They saw improvements elsewhere.
Correct. They also saw gains, maybe smaller but still consistent, of 1 to 3 points on things like creative writing, CWV3, and general knowledge benchmarks like PopQA and MMLUR.
Which brings us back to that RLVR comparison. The math models didn't generalize.
Right. But these RLMT models, trained on general chat prompts and rewarded using general preference data, they absolutely crushed models specifically trained on verifiable domains when tested on chat. They outperformed something like the math-focused DeepSeek R1 Distill by 10 to 25 points on chat tasks.
It really underscores that the kind of reasoning you learn is entirely shaped by the reward signal and the data you train on. General rewards get you general reasoning.
Precisely.
So the goal wasn't just to make models output a thinking step, but to make them actually think better in a way that helps with general tasks. Did they look at how the thinking changed qualitatively?
Yes, they did a qualitative analysis comparing the thinking traces generated by the model before RLMT, just after the SFT warm start, versus after RLMT optimization. And the difference was pretty stark. The pre-RLMT models, the ones just taught the format via SFT, often produce very rigid, linear checklist-style plans.
Like, okay, step 1, understand the request. Step 2, list key points. Step 3, write the response. Very mechanical.
Exactly. Very rote. But the models after RLMT training showed much more sophisticated planning strategies. Their thinking traces included things like, first, identifying and listing all the constraints of the request, actively mapping out the different parts of the solution space.
Okay.
Grouping related ideas into themes, and this is important, showing signs of iterative refinement within the plan. They'd link different parts of the plan together.
That sounds much less like executing a fixed script and more like, well, actual strategic thinking, the kind of back and forth, sometimes messy planning humans do.
Yeah, a good example they gave was asking the model to write a Twitter thread. The RLMT model's thinking trace didn't just outline the topic points. It first explicitly listed constraints like must be under character limits, no more than 5 tweets, avoid hashtags. Then it outlined the content. Then, crucially, it sort of ran its own plan through a checklist against those constraints, noted where adjustments were needed, and planned how to link the tweets before it even started writing the actual thread content.
So the planning became dynamic, self-aware of the task requirements.
Exactly. It was using the thinking step to anticipate problems and refine the strategy proactively.
And quantitatively, this extra effort showed up too.
Yes. They measure the length of both the generated thinking trace and the final response as RLMT training progressed. Both consistently increased. It suggests the model learned that investing more cognitive effort, longer, more detailed planning, was correlated with getting higher rewards from the preference model. It learned to think harder, essentially.
Makes sense. We should also briefly mention the data mixture findings. What kind of prompts worked best for training this?
Right. The ablation studies on the prompt dataset for the RL phase were revealing. They found that using a dataset called Wild Chat AD, which is rich in conversational and more complex general chat prompts, works significantly better than using datasets like ultra feedback or random subsets of Tulu, which apparently had more math problems or simpler instruction following or jailbreak attempts.
So the takeaway for people building these systems is if you want good performance on complex, open-ended chat,
you need to train the reasoning process using prompts that are actually complex, open-ended, and conversational. Garbage in, garbage out applies to the RL training data too.
Okay, wrapping up then. This RLMT research seems to really bridge that gap we talked about earlier between the structured, verifiable reasoning of RLVR and the more general preference alignment of RLHF. And it does so with a recipe that looks surprisingly efficient, especially with that RLMT 0 result challenging the need for massive SFT stages.
Definitely. It forces a rethink of the standard 3-stage LM training pipeline pre-train, SFT, RLHF. Maybe the lines are blurrier or the stage is less strictly necessary in that order. It also makes you wonder about where these improved thinking abilities are coming from. The qualitative analysis showed these really desirable planning traits, like iterative refinement and constraint mapping, emerging during RLMT.
Which leads to a really interesting question to leave our listeners with. How much of RLMT's success comes from just amplifying or unlocking reasoning capabilities that were already sort of latent within the base model? Meaning the base model could already think like that, but RLMT just provided the right incentives to bring it out.
Versus this. How much is it actually teaching the model entirely new cognitive skills during the SFT warm start, if used, or the RL phase itself? Are these emergent abilities learned during alignment or just revealed?
Understanding that distinction, amplifying existing potential versus learning new skills, feels like it could be the next big step in figuring out how to build even more capable and aligned AI systems. Something definitely worth thinking about.